Hello and welcome to this presentation on enhancing financial crime and compliance with machine learning for entity resolution and case similarity. My name is Marcel Gwerder. I'm a senior member of technical staff at Oracle Labs in Zurich. So yeah, let's give me a quick intro about me. I work at Oracle Labs in Zurich, Switzerland. I lead a task force on integrating research we do at the labs with the Oracle Financial Services Global Business Unit. So we build machine learning solutions for them. And we also work on integrating the Oracle Labs Data Studio and Oracle Labs PGX products. So today, what I'm going to talk about is I'm going to give you a brief intro on what the financial crime and compliance management means, about the whole process and its components. And then I'm going to talk about two different use cases that we have been working on in the last few months and years. So one of them is going to be entity resolution, and the other one is going to be case graph similarity in the context of financial crime investigation. So let's get started with what financial crime and compliance management means. So we can start with a few figures here to motivate kind of the importance of this field. The amount of money laundered globally is estimated to be between 1.6 trillion and $3.5 trillion annually. The 90+% false positive costing financial institutions billions of dollars in wasted investigation time each year. And we had over $321 billion in fines paid by financial institutions since 2008. So we can see there's a big motivation for us to improve the whole financial crime compliance management process and to incorporate sophisticated machine learning technology in those products to improve efficiency and accuracy for the investigations. So let's have a brief look at the financial crime and compliance management process and its components, just that you get an understanding of where the two use cases that I mentioned when continuing this presentation, the entity resolution and the case graph similarity use cases fit in. So the financial crime and compliance management process is basically a process that covers end-to-end business requirements across the whole financial crime and compliance value chain. So we start by customer onboarding. There we have topics on know your customers and customer screening. Then we have transaction monitoring and also fraud monitoring, making sure we capture fraud and we can generate alerts and then basically out of these alerts we can create cases to be investigated. And there we go to the case management component and further along the line to case investigation and then ultimately to reporting so that we can be compliant with all the regulations that are in place. And the two topics are entity resolution is basically going to be covering the whole value chain to a certain degree, but it starts at customer onboarding for sure. And we then also have the case graph similarity, which is basically a use case that is very specific to the case investigation. But we will see a bit more on that later. So one of the core components of this process is the Oracle Financial Services Compliance Studio, which is basically a integrated workbench for financial crime data scientists and investigators. It provides tools for getting access to machine learning and graph analytics and anti-money laundering scenario authoring as well. The whole system is based on Oracle Labs PGX, the graph analytics engine, and Oracle Labs Data Studio. And importantly as well, it adopts the financial crimes graph model where all the cases are represented as graphs. So you can see an example of a graph here on the right side with the different entities, transactions and relations between the entities. Yeah. So let's start with the first use case, which is entity resolution. So let's try to understand what entity resolution means and why do we need it. So you might be familiar with the ICIJ leaks, the offshore leaks, such as Pandora Papers or Panama Papers, where we basically have leaks of exposing secret offshore accounts of world leaders and celebrities and business leaders and billionaires and so on. So we have all this data available that basically documents, to some degree, financial crime that we can basically hook into. So the use case here is to use entity resolution to link a bank's internal customer data with those external entities. This doesn't have to be limited to offshore leaks like the Pandora Papers, but this can also be sanctions lists, watch lists, all kinds of external data that helps us with improving the financial crime investigation process and have a better and holistic understanding of our customers. So let's dive into a little bit of an example here, a more specific example, and let's try to understand what you're trying to do exactly. So on the left-hand side, you can see an example of a customer, and that would be part of a bank database, for example. And on the right-hand side, you see an example of an external entity that could be part of these offshore leaks, for example. So those entities, they usually share, similar attributes, but there's no common unique identifiers that you could use to just link to. So what we're trying to do with entity resolution is use these different attributes like names, addresses, and different attributes like date of birth as well, or the phone number and tax IDs to create a similarity edge between the two entities that represents the similarity between them. So since we don't have names that match exactly in this example here, we need to basically generate that score that indicates similarity. We cannot just do an exact match on the two entities. We will miss out on a lot of, identical entities, basically. So once we have the similarity edge, we basically create a global graph with it. We create these connections between the internal data and the external data, and we can then run additional kind of downstream analytics tasks on this data. So let's have a look at our entity resolution process. On the left-hand side, you can see, the different data sets, the external and internal data sources that we have and that we want to connect the entities with each other. Then in the middle, we have the entity resolution service, which is comprised of different stages here. So first of all, we have address parsing and address standardization. Those are basically just pre-processing steps to get the addresses in a format that we can use for matching the entities. And then we have a candidate finding step that aims to reduce the search space. So we then can do matching on a subset of the possible pairs of entities to reduce kind of the complexity of the whole operation and to increase the speed of it. And the ultimate goal is to have, a global graph representation where all these different entities are linked with each other, and we can have a, a holistic view of how they are connected with each other and what are the, similarities between them. So let's start with this first pre-processing step, just an example here to show what it does. So the address parsing and standardization step in this case. So the parsing basically takes the input address, which can be any format, and often they are entered in different systems on multiple lines, so they can come in all kinds of shapes and forms. So the idea here with the parsing step is just to separate the individual components of the address and be able to use them independently. So in here we're using a open source library called libpostal to achieve this. And then the second step is the standardization of the address component. So here we're trying to standardize how, for example, a country is represented. In this example, you see it converts the United States to US, or it converts Zurich into standard form here as well. So this will then help us to basically use exact match queries as well for this, because we then have the same representation, and that can help in the candidate finding step as well, which is the next one that I'm talking about. So candidate finding is meant to, as I said previously, meant to reduce the kind of complexity of the whole operation and reduce the search space and the different type of combinations we have. So in this step, what we're trying to do is we're trying to use a combination of exact match queries and fuzzy matching, string fuzzy matching queries that give us kind of a subset of candidates that we can then run the machine learning based matching process on. So this is currently all based on a search engine, so you could use OpenSearch or Elasticsearch or similar services to achieve this step. So as you can see, if we enter a query entity, we get similar candidates that basically have similar names or streets and identical country and so on. And we get the kind of preliminary matching score here for the candidate finding step. Then the next step is basically doing a matching, which, while the candidate finding is basically trying to reduce the search space but keep recall very high, in the matching stage, we're trying to improve precision, right? The matching stage is a more expensive operation. It only operates on a subset of entities, but it helps with increasing the overall accuracy of our matches. So what we do with our matching models, basically we use features that are based on distance metrics. So the user of our models can basically configure different distance metrics and how the strings are kind of split, and basically build a feature set that is tailor-made for their specific use case. And then we train a CatBoost model on those features that then has the goal of telling whether this particular pair of entities from the internal and external data set are a match or not. And it also produces an additional score. So how do those models fit into the pipeline? We basically get the candidates from the previous step, which was the candidate finding step. And we run those candidates through the name matching model and the address matching model. And then we get two additional scores. We get a score for the name matching step, and we get a score for the address matching step. And then what we can do here, and this is also configurable by the user, we can do a weighted average to get a weighted score that we can then use for the similarity edges. So in this case, we combine all the scores. We have the candidate finding score, the name matching score, and the address matching score, and we come up with a final similarity score that we can use in our global graph representation. So this already basically concludes the entity resolution pipeline. So just to summarize a few of the important steps that we discussed. The candidate finding stage basically focuses on reducing the search space while maintaining the high recall. You want to keep as many matching pairs in the candidate set as possible, but we don't really care too much about having some that aren't really matches in there. That's fine as long as we are able to reduce the search space enough. Then the next stage is the matching stage, and here we're using our machine learning models to improve the precision of the matches. So it's here where we filter out those kind of wrong combinations that came out of the candidate finding stage. So with this combination, we are able to improve the F1 score compared to the rule-based matching by 11%. So we can tell that the machine learning part of this really has a significant impact here. So still, we have some limitations on this solution. So the candidate finding can be slow depending on how it's configured because it's relying on string fuzzy matching. And the current matching models are specifically optimized for names and addresses. This can theoretically be used for any attribute, any text-based attribute, but currently we ship the models that are specifically optimized for names and addresses. Then the matching step kind of misses out on some additional information that we could derive from the graph structure. So I'm going to show an example of it in the next slide on this. So some of the ongoing research we have is specifically for addressing some of these shortcomings. So we are trying to speed up the candidate finding step by using a different approach. We're trying to use embeddings that are generated using transformer models, and then we aim to use kind of vector-based similarity search, which should be quite a bit faster than using a search engine like Elasticsearch and using string-based comparison. Additionally, there will be some overhead with generating or computing the embeddings in the first stage, but it will only be kind of a linear complexity there. We don't have to do this once per entity, and we don't have to, it won't affect the number of combinations, basically. Then another part that I mentioned is, incorporating this graph structure and using the graph structure to further boost the scores we have. So we want to increase or decrease the score depending on, where in the graph the entities are. Is the surrounding structure similar? And there might be additional, similarity edges between the two data sets that we can reach within the graph. So we want to use machine learning algorithms, graph machine learning algorithms here, and other graph algorithms to find out if we can actually increase the scores or get a better, matching accuracy here by incorporating those kind of details into the score. So in the picture above, you can see the person on the right-hand side that is circled in red basically has an additional connection through a company and another person with the other data set, and then there's basically a path that you can take and find that connects the two entities in a way other than the similarity edge that we created directly between them. So those kind of things we want to incorporate. All right, so that concludes the entity resolution part. So let's continue with case graph similarity. So this use case basically aims at improving the investigation stage of the financial crime and compliance management workflow. So investigators would get a case assigned that is a suspicious activity, and then they have to say or make a decision whether this is a benign case or not, or what kind of financial crime it could be. So they do so by using different tools within Investigation Hub, and this is kind of a notebook-based platform based on Oracle Labs Data Studio. And what we can do here in this particular use case, we can support investigators by providing them a list of similar past case graphs. That way they can basically inspect those past case graphs. They might have a decision on those case graphs already that they can use and incorporate in their decision-making process. So the goal of this kind of project is to find a way to find a list of similar cases that show similarities with the current case under investigation. So let's have a look at kind of the process overview here. So if we start on the left-hand side, we basically start with the case graphs in our database. So those case graphs, they include edge and node properties. And what we want to do is basically we want to create or compute embeddings for those case graphs, which we can then use to look up a new case graph. So we would feed those case graphs into a machine learning model that would compute and learn embeddings from those case graphs. We then create an index of those embeddings in our database. Then on the right-hand side, we can see, what happens when we have a new case. So we would feed that case into the pipeline, and we would use the trained model to create the embeddings for that new case under investigation. Then we can use these embeddings for that particular case to find similar cases in the embedding space, and we can list those cases along with kind of the similarity score in the notebook, in the Investigation Hub notebook. So one key component of this pipeline is basically the embedding model. And so let's have a look at a few requirements of that model. So this model must generate graph embeddings in an unsupervised manner. We don't want to rely on labels in this case. We want this to work on any graph, essentially. Then the model must be inductive, meaning we want this to work on unseen data without retraining the model. So if we get a new case graph, it should just be able to work as well as with the ones that we trained the model on with the past cases, basically. And then what we want to do is we want to also make sure that this embedding model supports edge properties. So this is particularly important in this use case because, transaction amounts would be edge properties, for example. So this would be a very important feature of our graphs. So how we are able to kind of meet these requirements. So our embedding model is based on unsupervised graph search, which is a graph machine learning algorithm that basically incorporates the neighborhood of a node to generate node embeddings. And then we train these models with Deep Graph Informax, which basically helps us to, discover structural similarities in the graph across the whole graph instead of just, one particular neighborhood. So if you have a larger graph, you can incorporate more of the graphs using that solution. But as I've already mentioned, like the graph search algorithm is for generating node embeddings. So what we also want to have is the edge property support. So we do that by kind of aggregating the edges that are connected to a node and incorporating them into the node embeddings. And then finally, we have kind of the readout stage where we aggregate all the node and edge embeddings together to get one kind of set of graph embeddings. So one important kind of takeaway from this for us was the impact of edge properties. So once we've added kind of support for these edge properties, we were able to increase accuracy for our kind of proxy task, which is crime type classification, by 23%. So this tells us that really the impact of edge properties is quite significant. So this is a few screenshots of how this would look like in the Investigation Hub notebooks. So on the top, you can see how we would list, the similar cases. You can see what the crime type is. You can see, how similar are those cases, and then a few statistics that could help you kind of understand why are those cases similar to the case under investigation. And then on the bottom, we can see on the left kind of our input graph, which is the current graph under investigation. And on the right-hand side, we can see kind of the most similar graph that we were able to find among the past case graphs. So you can immediately tell that the graph structure here is very similar. Obviously, those are different entities and different relations between them, but the kind of in the essence, we were able to capture this similarity well. So what are we currently doing? This is still a project that's kind of in progress, but we are able to prove that we can do what we want, that we can find similar case graphs using the graph embeddings and the similarity search. What we have not done yet is incorporate benign case graphs into our training set, because our training set was completely comprised of suspicious activity reports, which basically means they're already flagged as financial crime. So that's one of the aspects that we want to kind of improve and incorporate. Then we want to have a certain level of explainability. We want to be able to answer the question, why is one particular case graph that is shown by the system similar to the graph that we are actually investigating? Can we use some kind of explainability on the machine learning level, or can we show some statistics and user interface components that would help the investigator to understand why those cases are deemed similar? And then finally, we want to kind of move this into the product. So we need to work on the productization of these components and hopefully integrate it soon into Investigation Hub and Compliance Studio. All right, this already concludes my presentation. Maybe just to mention the work I've mentioned previously on entity resolution. That's already, the name and address matching is already available in Compliance Studio right now. We're working on incorporating address parsing and address standardization as we speak. And the case graph similarity work hopefully is released in Investigation Hub soon after we have answered some of these remaining questions. All right, so in case you have any questions, feel free to reach out. The email address is here on this slide. Thank you for your attention.